Let's talk about current ripple in this chopper. So previously we have derived the current expression in different time intervals. So here if we call it as kth time instant and we are calling this current as IL of k. So with this initial condition, when a voltage of Vg is applied, the current rises, so and it reaches to a value I L K dash at the end of this interval, where this is T on or D into Ts, whereas this is the switching time period. And we have established the fact that in steady state this IL of k plus 1 is equal to IL of k. Using this relation, we were able to find out the expression for the current IL. And after that, we tried to find out the voltage, average voltage across the resistance is equal to Vg into D, using the approximation that e power lambda Ts is approximately equal to 1 plus lambda Ts, where lambda is equal to 1 by time constant of the circuit, that is equal to R by L. So we have also emphasized on the fact that the time constant should be far less than the switching time interval, then only you can see such a linear rise and fall of the current. If the ripple in the current is small, then the ripple in the voltage is also small. Why? Because the average voltage is equal to inductor average current, which we have derived using ILK plus IL k dash by 2 into resistance. So now we'll try to find out the ripple current delta I. We are calling it as 2 delta I is equal to IL k dash, which is the peak value at the instant of t into k plus d into ts, k plus d into ds, and this is k. So at this instant, the current, when a voltage of Vg is applied, the current goes to a value of ILK dash. We already derived expressions for this, and we already found out ILK by equating IL of k plus 1 equal to IL of k. I'm just restating the same things which we have done earlier. So the definition of the ripple is this difference between the minimum value and the peak value, that we can write as IL dash k minus ILK. So we already have the expressions. I'm just giving out the expressions for 2 delta I is equal to IL dash k minus IL dash k into e exponential of minus r into 1 minus d ts by L. So if we simplify this, please refer to the previous video in order to get the exact equations for ILK dash and ILK. So the main intention of this particular tutorial is to establish the fact between ripple ripple current and the inductance. So as we go and substitute, we get an expression like this: r dts by L into 1 minus e power minus r by L into 1 minus t ts by 1 minus e power minus r by L into ts. So we are assuming r by L into ts is far less than 1, or time constant of the circuit is far less than switching time interval. Then we can approximate those exponentials with the first order Taylor series expansion, that is equal to 1 minus of r by L dts into 1 minus of r by L. Sorry, I'll rewrite this due to space constraint. So I'm just replacing the exponentials with their corresponding first order Taylor series approximations. So 1 minus of 1 minus r dts by L, this whole term, into 1 minus of r by L of 1 minus t ts by 1 minus e power minus r by L ts. Sorry, I have to replace it by its Taylor expansion. So 1 minus of 1 minus r by L ts. So when we go about and simplify that expression, we end up in Vg by L into d into 1 minus d into ts. So this is what the approximated current ripple, and if we try to find out its percentage with respect to the average value, that is, we found out this by taking the average of the minimum and maximum of the ripple. So if we try to find out this, we get 1 minus t into rts by 2L. So what is the takeaway from these expressions? So there is a trade-off between the minimum ripple that we can achieve and the inductance. The trade-off is, if we want a very small ripple current, either you can increase the inductance or you can decrease the switching time period. That means if we express the ripple content in frequency, I mean, just I'm rewriting this term in terms of f switching and L. If we, by increasing inductance and by increasing switching frequency, we can decrease the current ripple.